you all the notes last time. Get them. Go get them. All right. So, guys, let's dig in. We're on short time, and we're going to get into some mucky stuff. So, guys, let's remind ourselves where we were so that we can engage with where we're going at a similar level of depth and understanding. So, guys, last time in class we established some rules. They're in your notes, but I would encourage you to just mentally ascribe to or question these statements. So, guys, from chapter 5, we learned about heat being transferred. Yes? What did we learn about that? Well, we learned that there's two ways to get energy in and out of a system, heat and work. And in the absence of work, what do we call heat? Enthalpy. So now we've got this thing called enthalpy, and when we place ourselves in the system, if enthalpy, heat is going out, the change is negative, and if enthalpy, heat is coming in, the change is positive. And then, guys, we wrapped all that up with an interesting idea as we started to touch on this idea of spontaneity. And we talked about Bunsen burners burning, and we talked about balls falling, blocks falling, and we talked about nails rusting, and we talked about the idea that all of those things are spontaneous. We'll come back to it in a minute. But guys, we established this idea that those things are spontaneous, and the reason why is because they give off energy, those three examples, in the form of heat. Yes? You good? Please question if you're not. That okay? Okay. So then, guys, from there we said this. We focused on this idea of spontaneity, and we got into really weird conversations about smushing eggs against walls. Thank you, Michael. That's actually really interesting. But we started talking about smushing eggs against walls, but the bigger idea was about spontaneity and reversibility. Guys, pause for a minute and let those things reverberate in your brain. Spontaneity and reversibility. Check your notes if you need, but guys, it's very important that you understand the connections between these two. Spontaneity and reversibility. We're going to use that as the opportunity for Claire to... Are you all done? Okay, you can go out that way if you'd like. All right, so guys, let's talk. What does it mean to be spontaneous? It just happens. Happens on its own without interaction with the surroundings. But then I think Jonah and some others talked about this idea of forces. What about gravity? Doesn't that count? What about, we didn't talk about magnetism, but what about these fundamental forces? And we established that that doesn't count. That it's got to be physical interaction through the forms of work and heat. Those are our energy exchanging ways of thinking about this. The fundamental forces, gravity, electromagnetic, those aren't them. So we said, guys, that spontaneous, we're going to use the Michael definition, it just happens. So then we talked about what are things that just happen. We established that those are exothermic. And then, guys, from that point, we started talking about reversibility. And we said this, if a process is reversible, that means the forward and reverse processes go through the same pathway and they cancel each other out, so there's no net change. What are the only systems that are reversible? Equilibrium systems. Yes? Good? Okay. And then we said this, maybe we should ask this. Are equilibrium systems spontaneous? No. Because they're undoing themselves. And that's a confusion. Because people are like, wait, it's going that way and this way at the same time. So doesn't that mean dual spontaneity? And guys, the answer is no. By our definition of spontaneous, that is not equilibrium. So what is reversibility? And guys, what is irreversibility? And the answer is an irreversible process is a process that has a direction it always goes just by itself, and it has a direction it never goes just by itself. Those are spontaneous. And so then, guys, the idea that a reaction has a spontaneous direction, it always goes, but does that mean it can't be done in the other direction? Well, no, but it requires a different pathway with different amounts of work and heat. Whew. What do we need to talk about? Yeah, they're reversible. They're reversible. And so, well, yeah, Elizabeth, that's actually a really insightful question. And when we get into chapter 15 at first, but then deeper in chapter 17, we're going to talk a lot more about reversibility and how it ties to conditions and rate and all this other stuff. But for now, we just need to know that if something is at equilibrium, it's going in both directions at once. So we don't think of that as having two spontaneous directions. We think of it as being reversible, and then it doesn't fit into the conversation about reversibility and spontaneity. Is that okay? What else, y'all? Can you imagine trying to keep all of this straight, trying to teach it? It's redonkulous. Are we okay? Yeah.
So, spontaneous is irreversible.
Hold on. Yes, so spontaneous reactions by definition are irreversible, which means they have a direction they do go, a direction they don't go. But realize they can be reversed, just not on their own.
Okay, so that means equilibrium is not reversible. Or equilibrium is reversible.
Correct. Yes. Yep, you got it. Yeah. Keep digging. Are you good?
Yeah.
Okay, Claire. Yep.
With equilibrium, it's reversible.
Yes.
Could that happen without any outside
Right.
resistance?
Right, and that was the point that I tried to touch on that maybe we skimmed over too quickly. Because the misconception is people are like, wait a minute, does ice cube and water at zero, right? It's melting and freezing at the same time. Doesn't it do that without any outside intervention? Absolutely. Yeah, no question. It goes both directions without intervention. The problem is that when people think about that, they think spontaneous in both directions. And that's not how we think about it. When we talk about spontaneous, our narrow definition of spontaneous is has a direction it always goes and has a direction it never goes without outside interference. Is that okay? And you're right, and I think Elizabeth was maybe getting us to that as well. Equilibrium is not dual spontaneity. It just doesn't fit into the conversation. You good on that? What else, y'all? Clarification? You're good? All right. So, guys, let me pick you up with where we were. And, guys, we talked about this system that contains a gas. And we talked about the idea that when we open the valve between these two tanks, guys, this gas spreads out evenly. And we don't have to squeeze it. We don't have to heat it. We don't have to talk to it. We don't have to pray over it. Guys, it just happens. This goes there, and they end up equal. And guys, we touched briefly on this idea of microstates and averages and possible positions and half to the power of n, which could be Avogadro's number. But guys, the bottom line is this: why does this happen? And guys, you can get into the math your junior year in college, and you will. But guys, what you need to understand is that conceptually, the reason that this happens is because the bottom thing is more disordered. Mentally, if you want to tie that back to microstates, you could say there's a limited number of places where these molecules can be. Now there's more places where those molecules can be, and therefore the bottom state is more disordered, it's more random, because there's more places things can be. Good? So guys, if you're wrestling with that idea as we move forward, I suspect you guys are probably like my children. Left to their natural courses, your bedrooms are disasters. Yes? So guys, think about it. Like it literally, I cannot walk across my daughter's bedroom for fear of stepping on things. Like literally, after a week, you can't tell what color her carpet is. Like it's no longer visible under all of her volleyball kit and all her makeup and all her just crap. So, but guys, then she has to clean up her bedroom before she can leave for the weekend. So guys, think about this relative to microstates. When her clothes are in her drawers, literally those clothes have less freedom. There are specific places where they are and they're no longer free roaming. But guys, when her bedroom left to its own devices turns into what it does by Friday, it is literally high entropy. It's high disorder because crap is just everywhere. And if you were to grab some of her crap and throw it around, it still is just crap everywhere. Guys, that's chaos, that's randomness, that's entropy. And guys, that is where things tend to go. Left to their own devices, guys, processes tend to increase entropy. Now let's talk. What questions do you have about that? Yeah? Yes, that's the thing that's crazy. We're going to get to it today. You can measure disorder in joules. Literally, it is an energy. It is so what is energy? The ability to make a change, right? The ability to make things happen. And so literally, you quantify disorder in units of joules because it is literally an energy making things happen. And so you quantify disorder entropy in joules. Let me warn you right now, most of the math that we're going to do, enthalpy will be in kilojoules and entropy will be in joules. They're smaller amounts of energy, but yeah, you measure disorder in joules. Go ahead, because it can make things happen. Yeah.
So does that mean the bottom two have a higher energy?
That's an interesting point. Yes. So let's talk about this. Guys, this is important. Let's use Ivan's thought as a great connecting point. So guys, his question was, does that mean the system at the bottom has more entropy? And the answer is absolutely. This is more disordered than the top. Is that okay? Now, this is where we're headed with this. It says it under here, the second law of thermodynamics. Guys, what is the first law of thermodynamics? Energy, the law of conservation of energy, right? Energy is never lost or gained, it just changes form. Kinetic becomes potential, that's internal energy. And then system and surroundings, work and heat, that's conserved, right? Guys, there is not a law of conservation of disorder. There is not a fixed amount of disorder in the universe that we just move around like energy. Guys, the disorder of the universe is always going up. And we're going to talk more about that in a minute. So guys, this is the way the rest of the day is going to go. We're going to talk more deeply about how does entropy drive processes. Then, when we're done with that, we're going to quantify and do some math with entropy, and that will be our day. You guys ready to go? Okay. Barbara? All right. All right. No, I'm not asking if you want to see Barbara. I'm just trying to remember her name. That wasn't an offer. That was a question. Barbara. All right. Here, wait. We may not be Barbara ready yet. What did you guys call her last year? Kathy. All right. Here we go. Come on, Barbara.
When an ionic substance, such as sodium chloride, is placed in water...
Okay, have you guys seen this video before? Do you notice Eleanor's laughing? Eleanor, why are you laughing? We will see this video like 11 times. That is, in fact, the number. Guys, we're going to see this video. I literally believe that you could teach AP chemistry just by watching this video over and over and over again. No, we're going to. Eventually, you will memorize it. in the same way that missionaries know that they've learned the language because they dream in the other tongue. You will be dreaming this video. It really is going to become the very root of who you are as a chemist. We're going to watch it twice, right now. Okay, watch. This is just salt dissolving.
When an ionic substance such as sodium chloride is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions.
Bah! Would anybody like to be the Mila laugher? It is.
Surface and become
So, guys, just really, here, hold on.
separated in solution. Notice that water molecules.
So what are the forces that hold those together, the water to the ions? Intermolecular, not bonds, intermolecular forces.
Molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
You guys good? All right, let's do it again.
When an ionic substance such as sodium chloride is placed in water, water molecules
All right, stop. Guys, now what I want you to do is I want you to look at this freeze frame, this still, through the lens of disorder. And guys, please understand, we never talk about order in this class. It's disorder. Because if you think about this in terms of order, your signs change. It's always disorder. So guys, let's talk about the disorder in this picture. So guys, what are the two substances represented? Water and salt. So now let's talk about disorder. Which one is more disordered? Why the water? Explain to the person next to you why the water. Jonah, let's just stay there. Yeah, for now. Do you want to grab your stuff?
Yeah.
Okay, I like that you did that. Elizabeth, do you want to scooch over so that you can sort of stick your ear with Clara? And so guys, again, the question on the table is, why is the water more disordered or why is the salt less disordered? You guys okay? So what did you talk about? So bonds, okay, so, but we got a lot of bonds. I'm gonna be our group note taker. I think blue will show up okay. Let me make it a little thicker. So we've got bonds in here, right? What kind of bonds are those? Ionic bonds. We've got bonds in here, which are covalent bonds. So they all contain bonds, ionic and covalent, but there's bonding going on. But I don't know that that necessarily describes the differences in entropy. Go ahead, John.
The salt's less disordered because it has more structure.
Good. And that's actually is interesting. We'll talk about it later. Yes. So we have something like this, and to our eye, we understand that, right? Salt compared to water, this is much more structured, and therefore less unorganized, right? Less disorder. So, guys, does that sit okay with you? So let's then talk about it. If we were really to put this in motion, what are these ions doing? They're sitting there and wiggling. But what are they not doing? Moving past each other. Consequently, these have less freedom and therefore less disorder, microstates, right? Guys, what about inside of here? Mosh pit, craziness, right? More freedom, more microstates, more disorder. So are we comfortable with the idea only conceptually that the salt is less disordered than the water?
So if you're talking like a single
Good for you, yeah.
HCl being more
That's,
disordered because of that structure.
Yeah, so that's the thing that I didn't want to talk about. I said we'll talk about it later, but let's talk about it now. So let's take a water molecule. Did you hear Jonah's question? He said, what about the individual particles? And so this is where this gets really not fun in this horrible class, which again, I will hide from you. But it turns out that you have positional entropy, you have vibrational entropy, and you have, what's the name for it? It's like steric entropy or something like that. So the bottom line is when we talk about, but it's like positional. So when we're talking about individuals, like a water molecule or a formula unit of NaCl, but really when we think about NaCl, we think about the Nas and Cl separately. So it turns out that in a water molecule, you may remember that this angle is less than 109.5 because it's bent but tetrahedral and all of that good stuff, right? Yeah, we're going to go over that later too. Not this unit. But so the idea is that if we could look at a water molecule, let me grab a better example. If we could look at a water molecule, what we would find is that this is not always 104.5. This thing's going like this. It vibrates like crazy like this. So these things are doing this, and that's positions and therefore entropy, right? But at the same time, it's also doing this. This bond is extending and contracting and doing this. So there's vibrational entropy, and then there's this entropy, which I don't remember the name of. What's that? Is that in there?
It's my chapter summary.
There you go. Translational. Translational? Nice. Okay. So here we have mostly vibrational. These guys are locked in place and they're wiggling, and they probably, as a result, move a little bit translationally. But all of those factors play a part into the entropy of the substance, which then leads to a really weird question. What is the definition of absolute zero? What happens at absolute zero? There's no movement, right? There's no energy. But the actual definition of absolute zero is the temperature at which entropy becomes zero. Because energy is movement, right? And so at absolute zero, all the translational, all the vibrational, all the rotational, and by the way, this doesn't have rotational entropy. These can't rotate. These bonds can rotate. So at absolute zero, all of that energy is gone. Entropy is zero. So there's a weird connection. You guys okay? But what we really need is, guys, I got to turn this on. I can't see you. And so the thought then being is, guys, we just need to understand that it's disorganization. Go ahead.
So, looking at it with just like the one molecule,
Sure, yeah.
would the water have the higher entropy?
So that's the problem. Again, junior year in college. But it's more complicated than that. Because when you look at these individual things, remember, we've got moving electrons, more entropy, right? We've got mass. And what you're going to find out is that heavier things are wigglier, more entropy. And so there's factors for temperature, there's factors for mass, there's factors for bond strength, there's factors for interactions. Even the intermolecular forces inside of this change the entropy of the individual molecules. So the fact that we can quantify and model this is really quite fascinating, because there are so many different factors at play here that where was I? Calc 3 or DiffEq? Anyway, the math that it takes to actually think about this stuff is bonkers crazy, because there are so many interacting and many times conflicting influences that it's like a related rates problem from Satan. It's horrible. Like, it's really crazy. And so it gets even more. All we need to know, this is really the case. And guys, this is important. Don't miss this. You need to know that liquids have higher entropies than solids. I'm telling you that right now, right? Can we say it again? Liquids more entropy than solids? Can I say it one more time? Liquids more entropy than solids? When you take the test, half of you are going to screw that up on the test. I guarantee it. The reason that I'm telling you now is so that when we go over the test, I get to laugh at you and tell you I told you so. Is that evil?
Yes.
It's one of the few joys in my life, and so I reserve the right to do that. But guys, understand, there's a question on the test. Free response. And you're going to get it wrong because you forgot liquids have more entropy than solids. Okay? You'll see. All right. So, guys, coming back to this. Again, we're not quantifying, we're not rotational, vibrational, none of that. We just know that liquids have more entropy than solids. Good? Okay, now this. All right, Mila, this one's for you. I can get rid of that. All right, now guys, we're going to start again. Maybe? Oh, I'm drawing dots. We're going to start it. Liquids more than solids, right? Now, guys, I want you to look at entropy change. Okay? Here we go. We're now going to make a solution. Entropy change.
Water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules...
I muted Babs and she didn't shut up. Babs is all powerful. All right, so guys, again, entropy change. Now let's stop. Guys, and you can see that okay, right? What is happening to the entropy of the salt, the sodiums and the chlorides? It's going up, right? As the salt dissolves, the entropy of the salt is going up, structures breaking, ions are moving out. Guys, the entropy of the salt, does that sit okay? But guys, what's happening to the entropy of the water? It's going down. And guys, if we continue to play this video, this animation, now you see it clearly. Guys, the water's entropy has gone down because now its freedom has been decreased because they are clustered in some sort of positional structure around the salt ions. Do you get the idea? So now, guys, this. Now let's talk about how this works. Remember the conundrum? So guys, with these quick cold packs, was heat going in or out? Heat was going in, but it's spontaneous. So guys, why are these spontaneous if heat is going in? Entropy is going up. How much is the entropy going up? More than the heat that's going in. That's Gibbs free energy. We'll talk on Friday, but let's say it again. Guys, how does this work? Heat is going in, but disorder entropy is going up. How much is entropy going up? More than the heat that's going in. If that weren't the case, this wouldn't work. Huh? No, it takes in energy from the surroundings because it feels cold. Right, but entropy remember how we said there is no first law of entropy? Entropy is not exchanged. It's not like this is losing entropy to the surroundings. The entropy of our system is the stuff inside, right? So inside this, the stuff that's in here, so it's taking in energy. Its enthalpy is going up, but its entropy is going up more than its enthalpy is going up.
So that's literally just like making less energy in the room.
Yeah, so it's sucking, well, yes, but yes, so the room is losing energy. This is gaining energy. And first law of thermo, in a perfect world, that's the same. Energy lost is energy gained. So this is gaining energy, which means it shouldn't happen spontaneously. But it does because the disorder is going up more than the energy that's being absorbed. And we're going to quantify that on Friday. But guys, it's even more complicated than that, right? Just a second. It's more complicated than that. Because guys, those crystals and those beads inside of there are a salt. They're not sodium chloride, it's ammonium nitrate. NH4NO3. So imagine that the silver balls were the NH4s, and imagine that the green balls are the NH3s. NH4 pluses and NO3 minuses, ammonium nitrate. Guys, that's what's inside those beads. So it's really, I think I can do this. Yeah. Guys, it's really like this. If we could replace the silver guys with ammoniums and the green guys with nitrates, we got salt. We got that salt. And so, guys, where is the increase in disorder coming from? Because it's in water, right? When we broke this, we broke a bag of water. So we introduced water to the ammonium nitrate crystals. So who's experiencing that huge increase in disorder? The ammonium nitrate, not the water. The water is actually organizing, which brings up an even bigger idea that, guys, the amount of disorder that's increasing in the ammonium nitrate is greater than the energy that's going in, enthalpy, it feels cold, and the amount that the water is getting organized. So we have two forces fighting spontaneity, the organization of the water and the heat that's going in. But the entropy of the ammonium nitrate going up offsets both of those, and it makes it spontaneous. Correct. And so what is the spontaneous direction? Everything we see. Weird, right? You've never seen a non-spontaneous thing happen on its own. You've never seen a ball magically fly up in the air. You can lift it, but it doesn't happen on its own. What? But that doesn't count. No, you don't. That's the thing that's weird. Think about things that like our picture, right, of ice and water at zero. If you were to watch that, what would you see? Nothing. The ice never melts. The water never freezes. To our eye, there's no net change because they're offsetting, which is another reason why we don't think of it as being spontaneous. The net change is zero. And as a result, we don't think of it as being spontaneous. Yeah? This would be a good time to get a drink. Take your time. Not for you. Did you get it? What was your question?
Oh, I was going to ask you something like this.
Are you okay? Go ahead.
So, you said it has higher entropy, which is why it's cold.
No. Stop for a second. Let's pick that apart. So it has higher entropy, which allows it to be spontaneous, even though energy is going in as heat. Is that okay? Which may have been what you were thinking, but we need to be careful with words. Keep going.
So, for that ice pack, for hot packs, that means the enthalpy
Going out is greater. But then it gets complicated because how do hot packs work? And even how do ice packs work? Because you can also make an ice pack by just taking a bag of ice and fill it with ice, right? That's a physical change and not a chemical change. So this ice pack, cold pack, is a chemical change, and therefore the entropy and the chemistry becomes important. Is that okay?
So with the agree on with the ice example.
Yeah.
Last time when you were talking about the ice example, you said that it would like slowly change into a new shape because of the water and the ice.
Yeah. So yes.
So wouldn't that be saying?
Yeah, I mean, again, we can chase any of these examples until we just end up at a dead end. But even in a more controlled environment, the crystals would form similarly as well. So while I don't disagree with you, my fear is that chasing that idea down would lead us to incorrect understandings. Go ahead.
So, the amount of the entropy in the salt that goes down would be...
Hold on, let me think. The amount,
Entropy.
say it again,
The amount of entropy that the salt...
goes up. Yeah, entropy up. Good, okay.
The entropy of the salt goes up would equal the amount that the entropy of the water goes down and the enthalpy.
No. You ready? Can I use my hands too? I love what you're thinking, and the answer is no, and Elizabeth's going to hate this. You ready? Okay, so you just said the amount that the entropy of the salt is going up is equal to the amount of entropy going in and the amount of entropy for the water going down. The answer to that question is no, because you used the word equal. If they were equal, it would be equilibrium. Don't try to understand it. We'll talk on Friday. So if the total energy change in and out were equal, entropy for the salt, entropy and enthalpy for, you get the idea. If those were equal, it would be equilibrium. The fact that it's spontaneous says that the amount of entropy going up for the salt is greater than both of those. Yeah.
Anything that's not spontaneous has like a net change of entropy.
No, it could also be enthalpy, like burning a Bunsen burner. But and this is what Gibbs free energy does. Gibbs free energy lets us bring enthalpy and entropy together. And then when we bring enthalpy and entropy together, the thing that we can say for sure is that anything that is spontaneous is a net loser of energy, could be entropy or enthalpy, is a net loser of energy in the entire process. And that's what Gibbs free energy lets us do, and we'll do that Friday. Is that okay? Great question. Yeah.
So is formation or release energy because entropy is going down?
Say that again.
So when things bond, entropy goes down.
Yes.
Is that why heat formation is releasing?
That's a great, wow, Jared, that's an interesting question. So let's say it again. So yes, when bonds form, by definition, entropy goes down because we're losing freedom, right? So is that why enthalpy comes out? That's certainly related. The reason that I'm hesitating at first is because I think there's also a kinetic energy component to it. Because when things bond, they tend to slow down, right? To break bonds, we speed things up, right? So as things bond, they tend to slow down, thus a temperature drop, thus an enthalpy release. So I don't know that one completely explains the other. They are certainly related. The bonds form, entropy goes down. But I think there's also a heat, enthalpy, kinetic energy component because things tend to slow down when they bond. Is that okay? Okay, but also not something they're going to hold you accountable for. But a neat thought. You guys good on this? All right. So, guys, wow. We're now ready to plow on. You have the notes in front of you. Let me get caught up with you. And guys, all that we need to do then for the remainder of this little time together, and we are dangerously close, is this. Guys, and so here's the hazard. You have all the notes in front of you? So what I don't want to do is get bogged down in the words, but I definitely want to get bogged down in the ideas. So let's get started. So guys, this is what we know about entropy. It is the disorder of a system. But guys, do you promise me that you will never think about order because the signs are backwards? If randomness goes up, that's a positive change in disorder. It would be a negative change in order. That's why we have to think about disorder, because the signs matter. Is that okay? Okay. Then guys, we abbreviate entropy S. Obviously that makes sense for the same reason that we abbreviate enthalpy H, right? Good. Same system at work. So guys, the idea then is this, as we talk about change, the more disordered or random a system is, the larger the entropy. But guys, this brings us into something interesting that we should talk about right now. Let me stop here and let's talk. So guys, let's draw a distinction between enthalpy and entropy. How do we know that enthalpy is being exchanged? What do we see? Change in temperature. Is that okay? Guys, when we see an enthalpy change, we see a change in temperature. So we don't measure the enthalpy of a system. We measure enthalpy changes for systems because we watch temperature change. Is that okay? Now this. guys, you can directly measure the entropy of a system. Take its temperature, find its mass, figure out its structure, find out how much it can vibrate and rotate and translate, and we can find the entropy of a system. So guys, this is empirical. You can measure it and you can quantify it. Enthalpy is not. Enthalpy is a change, where entropy is an empirical value that you can quantify. You can look at this pen and go, how much entropy does that have? But you can't look at that pen and say how much enthalpy it has until it loses energy to a system, and then we can talk about its entropy change. Do you see the distinction? Okay. So guys, with that said, can you let your eye scan down the rest of the rest of the slide there? So it says, consider the following: the dissolving of water. Are we okay with the idea that it is spontaneous, and it's spontaneous because entropy is going up? The thought being that the salt is becoming more disordered. So guys, are we okay with all of these ideas? Yes.
So entropy going up is not synonymous, like pretty close to energy going out.
Good. So let's talk about, yes. Jonah's got a great thought. So entropy going up, not being released, but entropy going up is synonymous with energy going out. Absolutely. And the important thing we're going to talk on Friday is that energy going out, enthalpy going out, tends to be spontaneous. Entropy going up also tends to be spontaneous. So, and again, we'll talk next time, but if you've got a reaction that has a negative delta H, heat is going out, and if you've got a positive entropy change, that thing is going to be spontaneous every single time. There's nothing you can do to stop it, because both enthalpy and entropy are leading to spontaneity. Okay. Then if you've got a process where entropy goes down and heat goes in, it will never be spontaneous. And then we'll talk about the tiebreakers. Yeah.
So in the example of the ice,
Mm-hmm.
the entropy was going up,
Mm-hmm.
but it was still endothermic, so energy
Yes.
was coming out.
Right. Yeah, right.
Then in that case, are they not synonymous?
They are not, well, they're synonymous in that they are predictors of spontaneity. But in that particular example, they're competing with each other. So so ice pack, heat is going in. That doesn't favor spontaneity. Entropy is going up. That does favor spontaneity. And we know that the up is greater than the in because we know that it's spontaneous.
But it feels cold, wouldn't that mean that the heat is greater than the out?
It's not, because if that were the case, it wouldn't happen. So if this reaction did not increase entropy more than the heat that's going in, it would never happen. So the thing that again, spontaneous, right? We don't have to keep shaking it. This is a deep thought. But the idea is that the reason that this is allowed to happen and take in energy and feel cold is because the entropy that's going up is greater than the heat that's going in. If this didn't have a huge increase in disorder, this wouldn't feel cold because it wouldn't happen, because it wouldn't be spontaneous.
So when entropy is going
Did you
up,
say entropy or enthalpy?
entropy-
Okay, when entropy goes...
Disorder is
Yes,
going
good.
up.
Like that better.
Is that like is increasing the energy of disorder, but is the energy of disorder not ever manifested?
Do you really want the answer? Okay. So guys, Clara's question is, does entropy manifest itself in heat? Right? And the answer is no. But heat can manifest itself in entropy. Here, rub Lindsay needs a little loving touch. Let's answer Clara's question. Blame her and not me that we're talking about this at all, and then we'll summarize. No, but here's what's happened. Just do this really quickly. What is entropy? Disorder, right? Wiggliness. What causes things to wiggle more? Heat them up, right? So really many times, so entropy is self-guiding, right? We saw the gas spread out and it did it all on its own. Doesn't have to take heat. But if we were to heat up those gases, its entropy would go up because now they're wiggling faster inside their containers. So entropy being a force doesn't require heat, but if heat goes up, the entropy goes up too.
So having the cold, like it manifests as cold means that energy is coming in, which is increasing.
The entropy. Correct.
But that increase in entropy wouldn't cancel out.
Correct. Yes, that's it. That's good. All right. So, guys, let's have a big, safe Lindsay hug here. So, guys, here's what we know. Entropy is a very real driving force that causes things to happen. Guys, we understand that when we look at processes, like think about our Barbara video, guys, when we think about processes, we can no longer just talk, well, here. So guys, remember when we watched the Barbara video, we had salt and we had water. And what was happening to the entropy of the salt? It was going up. What was happening to the entropy of the water? It was going down. But guys, there is not a law of conservation of entropy. This went up more than this went down, which means the universe, literally the universe, is always tending towards states of higher disorder. Solids have less disorder than liquids. And guys, when processes happen, this is not conserved. Disorder can go up and there isn't an offsetting go down. Entropy is not conserved. It can go up and there isn't an offsetting down. Yeah.
Great, but entropy, enthalpy, and kinetic energy are all conserved. Are they not?
I don't know. Can we table that for a second? That's going to be something that we would really need to think through. Here's what I'd like to do. Guys, let's finish this slide. Let's hit pause. Let's come back and wrap this up, and then we're going to transition into lab. But we're going to need like 10 minutes after break, okay? So let's leave this as a place where we're safe. So guys, these are the deals. When we look at disorder, we got to consider everything. Not just the salt, not just the water. We've got to think about the entire things. And guys, many times these involve ordering and disordering processes. But guys, in things that are spontaneous, and again, Liz, this is a safe place to go. In processes that are spontaneous, the disordering, like the mucking up of the salt, is dominant over the ordering processes, like the organization of the water. Is that a safe place to land right now? Let's take a break. I'm going to pause. We'll come back and wrap this up, and then we'll do lab. Go get them. And we're back. Okay. Yes.
Where he makes your own entropy go up, and when does it go back down? Because there's no way you're like just so much more disorderly when you're like a baby.
Lindsay, if you want to leave, you're fine. We'll come and get you. I know, we'll come and get you. No, that's not sleep. But, yeah, I mean, everything that happens, right? I mean, cleaning our room is not spontaneous, but the reactions, the metabolism, that then make it happen and therefore are spontaneous, are processes that literally increase the disorder in us. And there's cellular repair, and there's all the things that undo that, but we're releasing gases that were tied up in sugars. Yeah, there's all sorts of increasing entropy processes going on inside of us. Yeah, it's crazy. Yes. I don't know if we should talk about that because I don't exactly know what happened, but yeah, anytime there... Yeah. All right, so guys, let's make this mathematical. We've got about 7 minutes. Then after the mathematical, we're going to talk about, and Linz, this is where it's safe to reconnect. Then after the mathematical, we're going to come back to the conceptual to make sure that we're clear, and then also talk about where this is headed on Friday. So here we go. Guys, this is the second law of thermo. But let's think about this in contrast to the first law of thermo. Guys, the first law of thermo is the law of conservation of energy. We have a finite fixed amount of energy in the universe, minus E is equal to mc squared. We have a finite amount of energy in the universe, and it just moves around. But guys, the budget sheet always balances. Kinetic and potential interchange, no net change. Work and heat exchange, no net gain or loss of energy. Lost is gained, system and surroundings. Well, guys, that's not true in enthalpy. There is not a limited amount of screwed up. As a matter of fact, and I don't want to dig into this too deeply, but guys, as we think about this idea of Big Bang cosmology, when that bang happened, if we ascribe to the idea that there was a moment 14 billion years ago when the whole universe was smushified into a single point, it was very, very hot, and therefore there was entropy. But guys, as that thing blew up, it expanded, and the positional and the rotational and the vibrational, guys, the microstates have just continued to increase and increase and increase. And guys, there's maybe not a limit to that. That this is just going to continue to increase into affinity. There is not a limit to entropy. So, as a result, guys, we've got to talk about something new. Have your AP equation sheets at the ready. Guys, when we talk about entropy changes, it is no longer necessary for us to think about system and surroundings, because the numbers don't balance. And so, guys, what we talk about is the entropy change of the universe. This takes into consideration the entropy change of the system and the entropy change of the surroundings. And so, guys, what we can then track is the entropy change of everything. Are we okay? You have it in front of you, so you should be thinking and not writing. Are we okay? So guys, the idea then becomes this, and this is where this comes back to reversibility. So guys, in a reversible process, which we understand to be an equilibrium process, the entropy change of the universe is zero. If you like the analogy, minus Jared's observation that as the water recrystallizes, it could take on a slightly different crystal structure. Guys, if you think about the melting ice and the freezing water, the net change is zero. For every, and I'm not quite ready for this, but guys, for every, we could talk entropy. So guys, for every molecule that freezes and its entropy goes down, a molecule melts and its entropy goes up, and the net entropy changes zero. Is that okay? That's equilibrium. Now, what about irreversible and therefore spontaneous processes? And guys, the bottom line is this: the entropy of the universe is always going up. I want you to stew on that for a minute. And then we can talk about Jonah's sarcastic and yet wonderful observation about cleaning his room. Yeah.
So, the universe is a spontaneous reaction?
Well, I mean, maybe. So anything that we have, anything that we experience happening, right? This is about to get metaphysical. But anything that we experience happening is by definition spontaneous. And because our universe is made up of only things that we see happening, right? We don't see the things that don't happen. Think about that tonight. So everything that we see happening is spontaneous, and therefore entropy is going up. Yep. Is that okay? Okay. So guys, let's talk about that relative to cleaning of the room. What is happening to the entropy of your room if you clean it? It's going down. But guys, it's happening. Your room is getting cleaned. So it's happening. So guys, what that means is somewhere in the universe, there is an offsetting increase in entropy. And in this example, it's all of the metabolic and biochemical processes inside of you that is turning your food into the ability to clean your room. Is that okay? Yeah.
So the only reason, like, I don't know, because like if you keep thinking about that, like the energy of the world would just keep going down and down. So
Yeah.
it's like the sun is providing.
That's brilliant. Let's talk about that. So, guys, okay. It's about to get worse. I know, here we go. Ease into it. So, right. So, think about, so Michael brought in this idea of the idea that the entropy, the energy, it's running out, right? So what is our source of energy here on the earth? It's the sun, right? And so the idea is that, take for example, a tree, a plant growing, right? As a plant grows, is the entropy of that plant going up or down? It's going down, right? A plant, you wait. Who said wait? Elizabeth, wait. Okay, so what? We're way simplified, right? This isn't biology, but fundamentally, what's happening inside of a plant is carbon dioxide gas and water liquid are coming together to form sugars and cellulose that then is a plant. So when plants grow, we're actually decreasing the entropy of the things that make up that plant because these free-ranging gases and liquids are becoming plant, and that's a decrease in entropy. Right. No, that's okay. So let's take the analogy. Follow my hands, and we'll make it in a minute. So if this is your room, entropy is going down. But if this is you, this is interesting. This is going to turn into an analogy. So if this is your room, entropy is going down. But this is you cleaning your room, and your entropy is going up. The molecules inside your body, the sugars are being converted to carbon dioxide and water, and you're exhaling, and your muscles are moving, and they're moving in positions, and now you have more entropy. And it takes all of that to clean your room. So the entropy of the room's going down, the entropy of you's going up. Now let's do it again. You ready? Now this is a plant. When a plant grows, what's happening to entropy? It goes down. So what is the thing whose entropy is going up? And the answer is the sun. So in the analogy, you are to your bedroom as the sun is to a plant. And so this is the idea. And you talked about sunlight, right? So we in our everyday experience are like, oh, the sun is a source of heat. It is a source of energy. Plants take that energy and they grow. And without sunlight, they don't grow. And that's true when we talk about heat and enthalpy. But if we talk about entropy, then when a plant grows, its entropy goes down. The things that make up plants goes down. And because that's happening, we know that there has to be an offsetting increase in entropy somewhere else. And that place is the sun. So as the sun, it doesn't really burn, right? It's fusion. But as the sun burns, the entropy of the sun is going up. It's expanding, it's radiating, it's wiggling. And as the entropy, as the sun does its thing, the entropy is going up. So assuming that that's our little world, that's just the earth and the sun, and that's where we get all our energy, the idea is that the sun is not only a source of heat and light and radiation and energy, it's also a source of entropy. Isn't that weird? Yeah, and that's the place where you can just start chasing your tail, right? And that's the problem with entropy, is that it's hard to talk about systemness when you talk about entropy, because really we have to talk about everything. We can't limit anything from the conversation. So yeah, as you're cleaning your room, the entropy of the atmosphere is going up because you're breathing more carbon dioxide into the room as you strip that out of your sugars that are allowing you to move. So this could go on forever, and but the fundamental idea is anything that is happening spontaneously, anything that's happening, there has to be a net increase in disorder in the universe or it wouldn't happen. And that's actually the second law of thermo. The entropy of the universe is always going up. Yeah. Hold on. You should clear this question with Lindsay. Is it okay?
Yeah, I don't like it all the stuff.
That's what I do.
So, for spontaneous processes, the is going up. But for a non-spontaneous process, would there be no change? Would it go up? Would it go down?
But remember, when you say non-spontaneous, do you mean equilibrium, reversible, or do you mean just something that's not happening?
Just something that's like, if you went and like broke something. I don't know.
Let's use the example of a rusting nail. Okay, so nails rust, energy is going out, there's an offsetting increase in disorder because it's happening. Okay. You know what? Hold on. Let's do something let's talk about cleaning rooms. Okay. So your room goes from clean to messy spontaneously. That happens all on its own, right? You don't have to you just have to live in there and it becomes a mess, right? But what about then the non-spontaneous direction? So the non-spontaneous direction, cleaning your room, right? That can happen. Generally at the threat of being grounded, but that can happen, right? Your parents can force the reverse process, but then at that point, you have to do work, right? So the idea is you just live in your room, spontaneously it becomes a mess. But so that's spontaneous and therefore irreversible. The non-spontaneous direction, the direction that it doesn't want to go, we can force it to go in that direction, but it requires work that we're not needing to do to make the mess. But that work that is required to reverse the process is leading to an increase in entropy in us because of all the metabolic things that have to happen in order to make that mess go away.
So will that always apply to like if the thing doing work is like the piston and the
Yes, absolutely. So maybe let me try this. So we've got condition A and we've got that'll be fine. Mess and not mess. Okay. And then say that this is the spontaneous direction and this is the non-spontaneous direction. This happens all on its own, right? Which means we have an increase in entropy. This doesn't happen on its own. It requires work and heat that this didn't. But we also know that because we can make this happen, this also requires an increase in entropy. So
from A to B, it doesn't need work. B to A, there's an increase in work.
yeah, only because when we're talking about A to B, we're talking about enthalpy, which excludes work. As you get deeper into this in college, you'll include work, but the rules don't change. Yeah.
And then so basically everything results in increase in
Mm-hmm.
except
Entropy. Yes. So the bottom line is anything that happens, whether it's spontaneous or not spontaneous, and we force it to happen, there will always be an increase in entropy. Are we good? All right. So how do I clean this up? Mila's going to laugh. Here. Are we good on these ideas? Where do we go next? Okay, so the idea then, guys, and you have this in your notes, the idea then is that anything that happens, be it spontaneous or not, it increases the entropy. So spontaneous chemical reactions, so you know what? Do you find this confusing? Let's read it. Therefore, a spontaneous chemical reaction, one that goes all on its own, spontaneous, that decreases disorder, like a plant growing, right? Maybe that clarifies. So if you have a spontaneous chemical reaction, like a plant growing, that happens. It must increase the disorder of the universe somewhere else by an equal or greater amount. And ultimately then, in that example, it becomes the sun, because the sun is, its disorder is going up. Is that okay? Okay. So guys, let's wrap this up and let's call it a day. Literally, let's call it a day. So guys, now what we need to do is we need to quantify this, and then we're done. So guys, this is the deal. When we talk about enthalpy, we can't directly measure it. We can't go to this pen and go, hey, how much enthalpy. When we talk about enthalpy, we can't directly measure it. So what we can do is we can take cold stuff and hot stuff and mix them together, and then we can talk about enthalpy changes as heat is transferred. Guys, that is not true of entropy. Guys, with entropy, we can figure out those values. We can go to that pen and we can go, how screwed up is this pen? How disordered is this pen? How random is this pen? How much entropy does this pen have? And then, guys, we can talk about what are called standard molar entropies. Now, guys, this should, forgive the pun, vibrate in your head, because we've talked about heats of formation. Now we're going to talk about molar entropies. So guys, grab your AP equation sheets. Does anyone need one? You're good? Jonah, you good? And guys, turn to page 4, thermodynamics. And guys, let's go through the list. The very top equation there in the bottom left is our MCAT equation, right? Been using that a lot in lab. Then guys, looking at the next 3 equations, you'll notice that they all look frighteningly the same. You've got sigmas, you've got products, you've got reactants. We already dug in deep to the second one, which is the heat of formation, delta H. Yes? It's products minus reactants. Remember, the N is missing because we multiply by numbers of moles, but they assume that you know that. And it's products minus reactants because the reactants are not forming, they're breaking, and therefore formations need to be flipped around. Good? Okay, now look down. Delta G. That's Friday. Now look up. Delta S. Not at me. Look up. Guys, delta S. Compare the delta S equation to the H's and the G's. What's missing from the right side of the equation? There's no change. Do you see it? On the right side of the equation, for calculating the change in entropy of a process, delta S, that's on the left. Guys, notice the values on the right are not delta S's. Let's compare that to the next equation down. With the delta H's, the values that we plug in there are heats of formation. How much energy is lost when water is made? How much energy is lost when methane is made? How much energy is lost when carbon dioxide is made? And then we flip around the reactants and add them all up, right? But those are heats of formation. How much energy is lost or gained when these things are made? Guys, with the entropy, dude, this is not an entropy of formation. This is not how much does entropy change when water is made. It's how much screwed up does water have just stinking sitting there. It's not an entropy of formation. It is an empirical entropy. Does that make sense? But guys, the bottom line is this. We use it the same in the math. Do I not have the equation up here? Oh, it's at the very bottom. Here, you see it down at the bottom, right? So guys, these are entropies. They're not entropies of formation, but I think, Joni, you asked, or somebody, I think you asked when you were back there, what are the units? And guys, the units are joules. Entropy is measured in joules, but it depends on 2 things, how much and how hot. Don't miss this. You may want to scratch notes to yourself. Guys, entropy depends, for now, you'll learn more in college, it depends upon how much and how hot. So the more of something that you have, the more screwed up it is. And the hotter the something is, temperature in Kelvin, the more screwed up it is. Is that okay? Okay, yeah.
Why would so the more something you have, the more entropy it is, right?
Mm-hmm.
Why would a big block of metal
Yeah.
have more entropy than like a little one?
Because there's more potential microstates. Each one of those places where a particle exists is a place that other particles in theory could move to, and consequently you have more disorder because you have more potential places.
But sorry, it's fine.
No, it's okay. Yeah.
Like theoretically, couldn't there be potential places for all the molecules to go to?
No, absolutely. But understand that so let's take our salt crystal. So, if forgive me for not ripping this apart, but imagine the salt crystal was just a sodium and a chloride. Okay, those guys are wiggling, right? And everywhere that they have to wiggle to is a possibility for disorder. Now let's talk about a crystal this size. Now we have more things wiggling. So at any moment, if we only had two, this guy could be here and this guy could be over here, and that would be a microstate, right? But now if we have more molecules or more ions, now this guy could be here, this guy could be here, but this guy could be up here. And now if this becomes the thing we're looking at, because we have more things that can wiggle to more places, we have more disorder.
So those two
You'll learn about this as a parent. They say that the minute you're outnumbered by your kids, the game is over, right? 1 is easy. 2 gets challenging, but you can play one-on-one defense with your wife and you're good to go. The minute you have 3, you're outnumbered and all hell breaks loose, right? Same idea. That once as the number of kids that you add to the family, the more chaos. Because literally each one of those kids can be doing different things. And so the more there is, the more kids there are, the more crazy in your house. Some of you are going, amen, brother. But that's the idea.
So, sorry,
No?
I'm going to try to rephrase this a little bit.
Okay.
So, it might not be that like the atoms themselves can be in different spots, but you could have the atom doing different like rotational.
Yeah, sure, and that just makes it worse. Yeah, you got it. All right. So guys, remember what I said to you about this idea that liquids have more entropy than solids, and you're going to forget about this? They'll still miss it. Guys, what I want to do then to wrap this up is to bring you to these guidelines. You should be able, given our conversations, to agree with these things. First of all, the entropy of elements is not 0. Let me just bring all these up. So guys, when you are plugging, I'm going to shut my board off so I can touch it. When you're plugging values into this equation, if that were the heat of formation equation, we said that the heats of formation for elements are 0. Because elements being formed from their elements doesn't make any sense, so their heats of formation are 0. But guys, elements can still be screwed up. So the elements have entropies when you're looking at satisfying this equation. Number 2, Michael's going to remind you, and you're still going to screw it up. Gases have greater entropies than liquids or solids. And then liquids are greater than solids. So these are in order. Then guys, number 3, the heavier something is, the wigglier it is. So entropy tends to go up with molar mass. Guys, entropy also goes up with the complexity of the molecule. And then guys, finally, molecules that are stretched out are more wiggly than molecules that are balled up. We're going to talk about this a lot when we get into intermolecular forces and phases, because it turns out that if you take a molecule like an oil and stretch it, it melts. And then if you let it ball up, it solidifies. Because, is that right? No. When it balls up, less wiggly, shorter, so it melts. So when it balls up, it melts, and when you stretch it, it solidifies. Because when it stretches out, it becomes wigglier, and then the wiggly things attract each other, and it forms a solid. We'll talk more when we get into this. But so guys, longer things have higher entropies. But think about it. It makes sense, right? If I'm curled up in a ball, but if I'm stretched out, then all of a sudden I can be more wiggly. And so entropy changes with elongation as well, yeah?
Wouldn't the higher entropy result in it coming?
No, and that's, the minute that came out of my mouth, I was like, snap, I shouldn't have said that. There's another related thing, which is intermolecular forces. And the greater the entropy of a substance, the stronger its intermolecular forces. We're going to get into something called instantaneous dipoles in chapter 8, but we'll get there later. Sorry, that might have been distracting. All right, you guys good? Yes, no, okay, sorry, no, stop, yes, thank you, no, bad me, bad. Guys, just remember, gases more than liquids, more than solids. Yes? Okay. I'm sorry. Sorry, man, I'm sorry. I jumped ahead and then I was like, oh snap, and I couldn't. Once it's out there, you can't take it back. Again, a marriage lesson. Once you say it, you can say you're sorry, but it's still out there, and your wife will say she forgets or that she forgives you. She actually doesn't. So, guys, are we okay? Lie to me and say it's okay. No, so guys, again, I apologize. Please do not let that thought, although I hope that when we talk about intermolecular forces, you'll come back to that thought because it's interesting and important, but right now it's not. So guys, forgive me for leaping ahead. Don't worry about melting and freezing and intermolecular forces. It's a different application. Just remember that let's go the other way. Gases have more entropy than liquids. Liquids have more entropy than solids. Damage done, undone? Okay. So, guys, this then becomes your homework. And I'm going to stop recording.